Section 6.3 looks at similar polygons. This is our introduction to what similar polygons are. We see our first glimpse of solving with them, and this is leading to identifying similarity by our three methods, which is in the next two sections. So let's start with what similar polygons are. So by the definition, two polygons are similar polygons if we have two things. The first is corresponding angles are congruent. Just like with congruent figures, or congruent polygons, corresponding angles have to match. So we have A to E, B to F, C to G, and D to H. So we have those four angle pairs, and let's write those out. So I have A is congruent to E, B is congruent to F, C is congruent to, what do we have, G, and D is congruent to H. So we get those four angle congruences. Secondly, the second thing we must have for similar polygons is corresponding side lengths are proportional. So what you spent the last few sections in solving proportions, this is where we need them. This is where we need them for our similarity. Corresponding side lengths are proportional. So let's match them up. Corresponding side lengths just means they're corresponding. So AB matches with EF, BC, FG, CD, GH, AD, EH.
Demetria Vincent Walker, please call the attendance office. Demetria Vincent Walker, call the attendance office, please.
So, when corresponding side lengths are proportional, these four fractions exist and they are all equal to each other. If one of them did not work or they did not turn out equal, then they're not going to be proportional. So they'll give us values, we'll plug them in, and we see that they all match. But these need to exist. It's not the sides are congruent anymore. That's congruence. Now we're at similarity. And even if we look at these two shapes, they're not the same size. It's the fact they are proportional, that's where the similarity is going to exist. Now, before we get too much further, we have to identify these two polygons we have. We have ABCD is similar to EFGH, and that is our symbol for similarity. It's just like our congruent symbol, we've just dropped off the equal because they're not the same size anymore, but they're still the same shape. So we're going to keep these same polygons as we go through and look at them in a few different ways. So let's talk about those side lengths being proportional. So I've kept the same labeling ABCD, EFGH. Angles may be marked a little different, but let's keep those same ideas. So now we're looking at those side lengths being proportional, and if two polygons are similar, then the ratio of the lengths of the two corresponding sides is called the scale factor. This is going to be a big term for us. So let's copy what we just had. We had AB to EF, BC to FG, CD to GH, and AD to EH. If I take those and now I have values to plug in, I get 20 over 25, 16 over 20, 24 over 30, and 12 over 15. So I plug them in to tell me, okay, corresponding sides are proportional. I plug in my values. Now I look at the fractions. What do you notice about all these fractions? If you don't see it, can you reduce them all? Well, 20 over 25 is 4/5. 16 over 20, 4/5. 24 over 30, 4/5. 12 over 15, 4/5. This is not a coincidence that they all reduce to the same thing. Now, we said earlier the ratio of the lengths of the two corresponding sides. Each of those sides has a ratio of 4/5. So that means our scale factor is 4/5 for for this case, it describes the ratio between the sides. 4 units in this polygon will be 5 units in this one. So that's a key value that's going to describe the relationship between the two. So if I have two similar polygons and they want me to describe that relationship, I'll maybe have to identify the scale factor. But we're also going to see that's going to be an important value for when we have to solve with proportions and maybe finding a missing value. Because maybe we don't know that 15 for EH, and we have to work through and start looking at proportions. So let's look at an example. So we have some triangles here. I have DEF is similar to triangle MNP. Now whenever we write the scale factor, the first triangle they give us, and really any proportions for that matter, the first triangle they give us we want on top of the fraction. The second one we want on the bottom of the fraction. That's going to lead to consistency, so we're able to identify when maybe we're talking about DEF and MNP as opposed to MNP and DEF. So, let's start out with just comparing some values.
There are still 14 staff members who have not posted a portion or all of their attendance. Please take care of this now. Thank you.
9 and 12 are corresponding. I can make those a ratio. 12 and 16 also corresponding. X and 20 are the final corresponding ones. I've written them out. Now I look. 9 and 12, 12 and 16. Can I reduce any of those? Well, 9 twelfths and actually 12 sixteenths both reduce to be 3/4. So that is our scale factor. It's the fraction that I can get any of the values to reduce to. Now, why x over 20 doesn't do that? Well, we don't know what value goes above the 20. So that's what we're going to solve for. So 3/4 equals x over 20. I can do cross product. I get 4x equals 3 times 20. 4x equals 60, so x equals 15. Now if I put a 15 back up in here, that would mean I would have 15 over 20, which does reduce to 3/4 our scale factor. So it's finding that value that would fit into the proportion. Now some of you may be thinking, maybe I don't want to factor or reduce my fraction and get to 3/4, and that's perfectly fine. I could have took 12 over 16 equals x over 20 and done the cross product. Numbers would have been a little bigger, but in the end you would still get to that same answer. But it's just nice. Maybe you need to find that scale factor, or we just don't want to use such big numbers. If you reduce the fractions ahead of time, it does make things a little nicer. So a couple more examples here. BKA, GKY. So I'm going to match up the corresponding parts. Now, BKA is our first triangle listed. So I'm going to put those values on top. So this is going to be the top. This is going to be the bottom. And I know it's a little backwards. The triangle on the bottom and the top. We've flipped them, but that's okay. We're still going to go through it. So it's good as we go through. If we're not sure with corresponding, we use the letters they tell us in the name. I have BK are the first two letters. So that means 6 is going to be corresponding to the other first two letters of the other triangle. So GK is 10. So 6 over 10 there. Next I have KA. That's 15 over KY, 25. And last, 12 over X. It's good to write out all of the proportions. At least gives you a start, and maybe you can find something to work with. Maybe you can see, hey, I can reduce 6/10 to be 3/5. That's also what 15 over 25 would reduce to. Regardless, I get 3/5 equals 12 over X. I do cross product. I get 5 times 12 equals 3x. 60 equals 3x, so x is 20. I'll go to my next one. Now I'm looking for x and y, but I still want to be careful when I match things up. LKA is the bottom triangle. LGY is the top one in the diagram, but again, we want to list this one first and this one second. So LKA. Let's start with LK. First two letters. That's 12. LD is the first two letters. That's 21. Then I have KA. See, KA is 8. Second two letters, DY, is X. Last one in each, I have a Y, and that goes with 28. Now, it's a good time to check, make sure. 12, 8, Y. Did those all come from the triangle LKA? Well, I look. They're in the right spot. LDY. Do they all have 21, X, and 28? I look. They do. So that's a good thing to check to make sure, because maybe if I flip one fraction here, that's going to throw everything off, and my answer's not going to work. So I'm going to go two at a time. I'm going to use these two to find X, and then those two to find Y. Well, wait a minute. Couldn't we reduce 12 and 21? Let's reduce that, and that's actually going to be 4/7. So let's take 4/7 equals 8 over X and do the cross product for that. I get 4X equals 7 times 8. 4X equals 56. So X would be 14. Now we'll do that 4 over 7 equals Y over 28. I do cross product here. 4 times 28 equals 7Y. See, 4 times 28 would give us 112 equals 7Y, so Y would be 16. So X is 14, Y is 16. Be careful when you set them up. As long as you get the setup good, it's just basic proportions and solving, but it's matching up, making sure the corresponding parts match up, the sides, and you're setting up the triangles in the correct order. So we're going to keep that idea with scale factor. We have a couple more ideas to mention here. So first I have perimeters of similar polygons. Again, I have my same polygons, A, B, C, D, E, F, G, H. And earlier, well, let's read it first. If the two polygons are similar, then the ratio of their perimeters is equal to the ratios of their corresponding side lengths. What I was just getting to is that earlier we said this is what we call the scale factor. So we already did this, and we said the scale factor for this one is in fact 4/5. So what this theorem is saying that if I took a ratio of the perimeters of A, B, C, D and E, F, G, H, it would have the same ratio as the scale factor. It would be the same. So let's look. So I want the perimeter of A, B, C, D, and that's over the perimeter of E, F, G, H. So A, B, C, D. Perimeter, I'm going to add 20, 16, 24, and 12. Then bottom I have 25, 20, 30, and 15. The top values add up to 72. The bottom values add up to 90. I have to reduce that. Well, I look, they both go into 9. 9 I can divide out of both, so I have 8 over 10, which I can then divide by 2, and I get 4/5. So that's the ratio of the perimeters.
Johnny Lopez, please call the athletic office at 71329. John Lopez, please call the athletic office at 71329. Thank you.
So our ratio of the perimeters is 4/5. It's like what we promised in the beginning. It's the same as the scale factor. So they are the same. Now, where we might need this. Let's say I knew 4/5, and I knew one of my ratios was 72, and I wanted to find maybe the ratio of EFGH, because maybe I didn't know these values to start with. And I could go through and try to figure out the values, but if I know one ratio, or know one perimeter, and I know the ratio, I could solve with cross product and get to it. So that's the option it gives us to solve. If we couldn't find perimeter, we could get around that with the scale factor and knowing one of the values. Our last part here is, so far we've talked about the side lengths matching up. We've talked about the perimeters matching up to the scale factor. Last, we just kind of get a little more general. If two polygons are similar, then the ratio of any two corresponding lengths in the polygons is equal to the scale factor of the similar polygons. So we've talked about sides. We've talked about perimeters. Maybe some other things we may have. Altitudes. We may have medians. We may have mid-segments. It's any types of lines or measurements we could have in those triangles that also fit to the scale factor. So we have an example down here. I have two triangles, TPR and XPZ. I want to find the length of the altitude. Well, the altitude here is PS. Well, I want that value, but it's not a side on the outside, but I can still work through and use my scale factor to get there. So TPR to XPZ. Well, let's take a value from TPR. Let's take the 6, which is TS. Looks like TS is corresponding to XY. So TS will be 6, XY will be 8. So that means my scale factor would be 3/4. Now if you're thinking, well, he didn't use a side, he used a segment of a side. If I did 12/16 from TR and XZ, well, that would still come out to be 3/4. So it still works the same. So I use that 3/4 and set that equal to PS over its corresponding value, or 20. So 3/4 equals PS over 20. I do cross product. I get 3 times 20 equals 4 times PS. Gives me 60 equals 4 PS. So PS would be 15. So my altitude there would be 15.